Good afternoon, Europe. My name is Jacob Weistrom, and I'm a developer at COMSOL. I work from our Boston office in the US. So this webinar will focus on what's important when solving larger problems in COMSOL Multiphysics. For larger problems, the CPU time and memory usage become significant. If you haven't experienced that yet, you will when you increase the problem size. Since these are naturally limited, we call these resources in this presentation. COMSOL is using a hybrid model for parallelization using shared memory and distributed memory. We'll go into what that means, and I will take questions after the shared memory parallelization part, and of course after the end of the presentation, which will be about cluster computing. I will discuss the importance of linear solver technique, as well as what can be done if the memory requirements become too large for the machine you're working on. I will present new benchmark results, exciting new results for the newly released version 5.6 compared to some old releases. This will take a bit more than 45 minutes, so be prepared for that. I will be taking up questions at certain points, as I mentioned. So solvers for the layman means here stationary time-dependent eigenfrequency solvers, etc. The solvers on the top levels. At the core of their business, at least when we're using finite element formulations, all the solvers in COMSOL Multiphysics are doing an assembly of one or more Jacobian matrices and one or more residual vectors. At least one Jacobian and at least one residual. Think of a stiffness matrix for a structural mechanics problem and the loads. There you have the simplest case. And at the core of any of these solvers, you will have to solve for one or more linear system of equations, here depicted as AX equal to B, where A is a large matrix, X is a vector of unknowns, and B is some known right-hand side vector. So for the structural mechanics example, A will be the stiffness matrix, and B here will be the loads, and X the unknown displacement, the degrees of freedom. So to predict the memory requirements, which is one key resource for a particular case, is not easy. This graphs here illustrate the problem where we have 5 different cases, and for the 3, 4, and 5 cases here, we can see that the memory requirements grow mildly when we increase the problem size. But for cases 1 and 2, they grow rapidly. So what is the reason for this, and what can we do about it? And what we have done here, we have taken 5 test models with a particular solver configuration and then refined the mesh and inspected in the log or or with the task manager how much memory is used for these processes. And notice here that case 2 and 4 here only differ in the way they solve the linear systems. Case 2 is using a direct solver, and case 4 is an iterative solver. Case 1 and 5 are both modeling heat transfer, and they're both using an efficient iterative solver. In spite of that, they behave fundamentally different when it comes to memory requirement. And the difference is that case 1 is modeling radiation, heat radiation effects. So if we're working, for instance, on a machine with 64 gigabytes of memory, how many DOFs how large problem can we solve for? In the case 1, we can only solve for around 26,000 degrees of freedom, while case 5, we can go over 10 million degrees of freedom. So tremendous difference. First of all, we need to understand something about matrices. Matrices coming from finite element method are sparse, as we say, but the worst case scenario is that they fill up for different reasons. So the matrix dimension is n by n, where n is the number of degrees of freedoms. And the worst case scenario is that we have to store all these entries in the matrix, and they are complex valued, which means that each entry is 16 bytes. So on a 64 gigabyte machine, just to store the matrix would require, we can only solve a problem of size 130,000 degrees of freedom. And then there is no space for anything else, no space to post-process, represent the mesh, geometry, etc. So but that's a hard limit. Luckily for finite element method, the matrix is sparse. And that means in practice that we only have to store a fixed or a finite number of entries per row or column in the matrix. And that is used when we represent matrices in COMSOL, a sparse matrix format. On top of that, the solvers and the assembly are using more memory than just the matrix itself. For instance, the direct linear solvers are using LU factorization, and the extra memory needed is called fill-in. It's a fill-in effect. You might remember that from linear algebra in school, that the LU factors can be less sparse than the matrix itself. That's just an example. So in an actual COMSOL model, how can I determine the size of the problem, the memory requirements? Yeah, that is not easy, but let's first at least start to figure out how large my model is in terms of degrees of freedom. So as you know, might know, the number of mesh element is important here, because the finite element method is using a discretization directly related to the mesh elements. And on top of that, we can have multiple occurrences of a degree of freedom for a mesh element. We can, for instance, represent not just scalar values as a temperature, but we can represent the velocity and field values that are vector valued in general. On top of that, we might handle multiphysics coupling and chemical species and etc. To further complicate the picture, we can use higher order representation for basis function in the finite element method. For instance, second order Lagrange basis for a tetrahedral element for a scalar variable will result in 10 degrees of freedom for just one element here, mesh element. On the other hand, if we go down to linear basis function and use, for instance, for fluid flow, we will need both pressure and velocity representation, and we have 16 unknowns for a tetrahedral element. This is not the full picture, because for continuous finite element representation, these degrees of freedom are shared with neighboring mesh elements or finite elements. So we are, it's not clear cut how to figure this out. Luckily, we can use COMSOL to do the counting for us if we really want to know. So I've opened a model from structural mechanics library here. And the first thing we can do to figure out the size of the mesh is to find the mesh node in the model in the component of interest, right click and find the statistics option. That will give you not only an overview of how many elements you're using, but also the distribution of these and the quality of them. etc. But for our purpose, the size here is important. We are using 61,000 tetrahedral elements in this case. We can change the mesh and be on top of the statistics. Degrees of freedom was a different thing. And to find the size or the number of degrees of freedom we have in the model, we can find the compile equation node in the solver sequence. Notice that contains already a mesh selection with this section here. So that directly affects the size of the problem. We can also here find a statistics option and choose that. And that will look at the current model's complete multiphysics formulation for all the components in the model and give an overview in terms of degrees of freedom and also a total count. Now, next, parallelism is used to handle the limited resource problem, both to solve your problem faster, but also to limit the memory requirements. The first type of parallelism we are considering here is the one you obtain with standard multi-core processors. That is per default always enabled in COMSOL, and you can use less cores than your available physically, but then you need to downgrade yourself. Per default, we're using all cores. Here we are talking about threads, but threads is a software version of cores, and you can see threads equal to cores when you're using COMSOL. And there is also a concept like hyper-threading that is not used by COMSOL. So the parallelization works through the available cores on your multi-core processor. We will discuss that a little bit further. Here is a little bit deeper look at the multi-core processor. This is a quad-core CPU and showing one socket. And here you see illustrated 4 different squares depicting the different cores. But the key here is not the cores. The cores need to be fed with data, as we say, and that is done through memory buses. And the memory buses can access a number of memory banks, here populated partially with these red squares. And then you have empty slots for these memory banks. And this is a common configuration where you have at least as many cores as buses, but many processors today have more cores than memory buses. And that can generate a bottleneck. The memory buses for finite element computations are very often the limiting factor for performance, for parallelization on multi-core machines. And the reason is that what we have discussed, namely that for larger problems, representing the matrix and performing the assembly operations requires most of the memory to be used for this, which means that this is very memory intense operations to perform the assembly and perform the solution step. Therefore, the buses become typically the bottleneck. The benefit of doing multi-core or parallelization in general is that we can reduce the solution time. And a simple way of looking at this is that a certain part of the total simulation time is serial. We call that S here. It's the fraction of the total work that is done in serial. And the rest we can parallelize, the fraction of parallel work. And if we denote T here as the time it takes to solve the problem of a certain size with P cores and create this fraction, this is called the speed up. So we compare what it takes to solve the problem with one core with P cores. and we'll get the number larger than or equal to 1, hopefully. There are also a term here that, or a part here that is not included. This is an idealized picture, that an extra cost for doing the parallelization. You can actually get the speed up that is less than 1 if the cost for parallelization is high and the parallelization work is small. However, for most larger problems, there will be a fraction, a serial part that is rather small. And before we reach 1 over p here, or 1 over p reaches the serial fraction, we will get the speed up close to proportional to p. But eventually it will saturate the speed up to this fraction 1 over the serial part, and that's called Almdahl's law. So there is an inherent limitation to parallelization that has to do with the fraction of serial work. And what is serial and what is parallel? Well, for instance, the two dominating processes when solving a problem, the assembly and the solving linear systems, are heavily and intensely parallelized by us during 10-15 years. We have focused on these parts. And then there are other parts that are inherently serial. For instance, reading or writing to file, initialization of certain data structures, allocating memory is an inherently serial operation, for instance, etc., etc. And on top of that, as I mentioned, to perform the parallelization gives a bit of overhead. So administrating the parallelization requires extra memory typically, but also time at certain synchronization points to make the parallelization safe and correct. Here is an example of multi-core effects. So I have here a standard CFD model, laminar flow, static problem, stationary problem for 500,000 degrees of freedom. We compare the memory usage and CPU time to solve this problem in version 5.5 and version 5.6. You can see that all numbers are improving in the latest release. You can also see here an important effect, namely that to solve the problem with more cores requires more memory, and this is something we will get back to. So the main reason to use multi-core is to get speed up. There is a cost to do this, and it's a memory overhead. And you see here the speed up numbers are improving. Let's see what happens if we solve the same problem on a finer mesh. So 1.36 million degrees of freedom. We get a little bit better speed up number. We have still an overhead of almost 2.6 gigabyte extra to solve on 28 cores compared to 1. On the other hand, it takes less than 2 minutes to solve on 28 cores, so it pays off pretty well. Even larger problem, almost 4 million degrees of freedom, where the speed up close to 9 in the latest release, and we are using less memory than before. So you see on 1 core is basically the same, but the memory overhead to go up to 28 cores is 3 gigabytes less, and the CPU time is significantly reduced as well compared to the earliest the last release. The hardware is also important. It's not just the solver technology. We see here we compare 2 different dual socket CPUs with each 6 memory buses per socket. The more modern hardware is performing best, using 28 cores, 231 seconds, beats even the 32 core simulation with a little bit older hardware. So you see the number of cores is not the full story. It's also the type of hardware we are working on. You see the same type of speed up 8.6 obtained for using all cores for this. This was the bigger problem, the biggest problem. So multi-core computing is more beneficial for larger problems. You will see a better effect when the problem is bigger. And it gives them a significant effect on the overall CPU time. We will get back to storage of the files when the size increases, because it's a both on file and yeah, for the final MPH file, but also other related data that you might want to save from your simulation. So the most important part or the crucial part for memory and CPU time requirements are the last bullet here, but meshing can also be an issue. It's not always the computation itself. It can also be preparing, the pre-processing as it's called, of the simulation by creating the mesh itself. But in most cases, the solving part, the assembly of the matrix and residual vectors together, it almost always come in conjunction, computing the solution to the algebraic equations. These two steps are most resource demanding. So what can we do now? I mentioned that the multi-core parallelization takes a bit extra memory. What else can I do to reduce the memory requirement? First of all, there is a knowledge base entry on this, which you can read after this presentation to learn more. Common standard classical ways to reduce memory is to exploit symmetry, to remove details in your geometry, which sounds dangerous, but sometimes that can be done without sacrificing accuracy. And for that, you can use CAD tools to do what's called defeaturing or apply virtual operations. Another technique could be to, instead of meshing thin features, thin channels, you can remove them with boundary conditions instead. That's a modeling problem, and it can be supported by the physics interface you're working on, or you might have to do some modeling yourself. Sub-modeling is something I will show you what that means, and using assembly meshing. Assembly meshing means basically that you mesh the geometrical parts independently and then connect them with assembly with coupling operators, and that can be done automatically. But the default way of generating a geometry is by joining parts, and then the mesh, you lose a bit of meshing freedom by doing that. So that's an option. Discretization, we discussed that as an important part for the size of the problem. We can sometimes make the mesh coarser and lower the discretization order. I will give you some warnings when doing that soon. Using another solver, we saw introduction-wise here how an iterative solver can be much more efficient than a direct solver, and I will show you more of that soon. Enable out of core when you use a direct solver. We have an automatic option, but that can sometimes be overridden, and use it more extensively by enable it manually. Other ways is to trade in memory for a little bit more simulation time, and I will show you how to do that. Sub-modeling, we have blog posts, we have examples in the application gallery for this. It's an old technique. It basically is the following. You solve the problem first on a coarse match, which you can afford, and you take that simulation to feed a more detailed simulation. So the more detailed simulation is using the coarse simulation for boundary conditions and maybe even initial values to solve a more detailed simulation for a part where you know that the mesh resolution is important. This is the technique that not always works. The problem has to be forgiving in certain sense. Thermal conduction, structural mechanics, electrostatics, and diffusion type problems can typically be attacked with submodeling, but for more complicated problem, it might not work. Coarsening of the discretization. You can use physics-based meshing by applying a more coarse mesh to your problem. That will have an important impact on memory requirements. And as I said, geometry defeaturing, you might want to go down in order. If you are using higher order than the lowest, then lowering the order will reduce the size of the problem and also improve the sparsity of the matrix. And coarsening the mesh typically leads, of course, to reduced accuracy, but it can also lead to reduced robustness. For instance, if the physics you are working on requires a certain resolution, that's important for sensitive nonlinear problems, for instance. Lower discretization order is often a better way to start, but since it can even increase the robustness, many sensitive problems come from the fact we're using higher order discretizations. CFD is a good example, but CFD already uses lowest order discretization, linear. So in that case, the last option is not there for CFD. We have an out of core option that is automatic, which means it will kick in if you are getting close to the physical memory for your LU factorization, but you can override that if, for instance, if you're using several direct solvers and you want this to kick in earlier, or if you know that you have other memory expensive operations, then you want to reserve more memory for those. And it can be seen as an solver or replacing the virtual memory algorithm from the operating system to a solver one. So the idea behind out of core is to offload the memory to disk before the operating systems kicks in and flushes the process data to the disk with swapping, which is often very detrimental to the performance. So this is if you are using direct solver, this is an important aspect. And you can control here under the preferences where out of core solver and are storing its data. See to that you have enough space, and also preferably that it's in a local and fast disk drive that you're using. Okay, let's now come to linear system solvers and compare them, because they are rather different when it comes to large scale computing. Direct solvers are known to be robust. They don't need much tuning. They are what's called black box. They work for all kinds of matrices, but the memory requirement increases quickly when the size increases. And the factorization is usually is by far the most expensive part. When we have factorized the problem, the matrix, we can solve for several right-hand sides rather quickly, and that can sometimes be exploited for certain problems. The iterative solvers, they scale much better with increasing size. However, they need what we call physics-specific preconditioning. And that is the key to the robustness and also to the performance of an iterative solver. And it's not as robust. It's not the black box technique. Therefore, comparison between these is not trivial. It's not just to choose direct and iterative and compare. The preconditioner is the key to the success of an iterative solver. But when they work, they are optimal. We can show that with multigrid, for instance, it's an optimal technique to solve linear problems. So it's definitely worth investigating if it applies to the problem class you're working on. So when we say scale badly, direct solver when we say that the direct method scales poorly, this is what we mean. We have two aspects. We have the CPU time and we have the memory to store the LU factors. And in 2D, it's not too bad. In 2D, you can safely, rather safely, use direct solvers. But for 3D, it scales not as well. First of all, and becomes larger for 3D problems naturally, but the scaling law here, the power here is important. And I will illustrate that soon. This is for idealized meshes, which are like a cube in shape, but this is also the typical behavior you obtain. So to switch between those two is nowadays not so difficult in COMSOL, because many of your models will come with a suggested solver of the other type. So for instance, if you are using a direct solver per default, it will be you will typically find the suggested iterative solver together in your solver configuration. Let me illustrate that in the model I showed you before. Here is an example where both a suggested iterative and the direct solver come with the generation from, in this case, solid mechanics. And I can, as easy as this, use the other option. I enable the direct solver instead, and I'm ready to go with the other technology. And so adding a direct solver is easy to a solver sequence. You just right click or make it enabled. But adding your own iterative solver is something we discourage you to try out unless you are really into iterative methods. But luckily, most cases you will have one there, and it's as easy as this, and right click and enable, and you have one. So that's worth investigating if you want to take the jump to another linear solver technique. So why should you do that? Let me try to convince you. Let's look at a simple problem, a classical problem, structural mechanics, linear elastic material. And I'm looking here at the full wheel rim geometry to get a larger problem. I compare a direct solver to an iterative solver. We look at just one angle. This model comes with several configuration angles and load angles, but we just look at one here for illustration purpose. So here is a table where I've used a modern state-of-the-art iterative solver with preconditioning. Compare that to MUMPS. I know MUMPS can be beaten by Paradiso, but in this case, I just wanted to show the behavior. It's not dramatically different with Paradiso. You see here, the first two columns is the CPU time, and the last two is the memory requirement. And you see here that I was able to solve this problem on my 64 gigabyte machine up to 4.2 million degrees of freedom by refining the mesh to finer here. But not without effort. So out of core option kicked in automatically, and that worked pretty well. I can, it did not kick in automatically. I think I had to enable it manually, and that works well here. But without doing that, I got an out of memory. Right, without out of core, I got out of memory, and a way to get the simulation through here was by disabling the pivoting. The pivoting is costly from memory, but it also improves robustness. In this case, I could avoid that and get the simulation through using 57 gigabyte. On the other hand, the iterative solver only used 13 gigabyte and solved the problem in a fraction of that time. And if we compare the CPU time, for instance, for this problem when refining the mesh, you can see the green curves here are from the 5.5 version, and the blue are the new version. You see here that I have both the direct solver behavior on top here and the iterative solver behavior on to the right, the more benignly leaning slopes here. So for all problem sizes, the iterative solver is beating the direct solver, both memory and CPU time. Okay, so that was the technology for linear solver, the linear solution process, linear system solution process. Other ways to affect the memory requirements is to disable a number of mechanisms that are made to speed up the process, but they cost a little bit in terms of memory. I will quickly go through them. You will find them on the slides afterwards. They are not so interesting to go through, but you will have settings for on the linear solver side, both for direct solvers and for iterative preconditioner. You will have preferences settings on the preferences for multi-core computing. You will have settings on the advanced solver node for how to assemble both the block size and the use of the sparsity pattern. You have a new option in 5.6 to use something called memory scalability optimization for assembling, which if you're using many cores can also save memory. It's not enabled per default, so that you can then go in and enable manually. It's used for cluster computing per default, but not for multi-core processing. And then, of course, last resort, you can buy more memory. You can see to that out of core is enabled. And if you have access to an FNL license and a cluster, you can use that. So on cluster computing, you need another type of license to run. And that will give you memory benefits, and that's what I will discuss next. So far I haven't seen many questions on. Let's see here. Before I go to cluster, I will check questions from you. I got the question here. How does one turn on the sparse calculation in COMSOL? Well, the sparse representation is default. We have an automatic, that's a good question actually, because we can also represent the matrices in a full non-sparse way, but you will automatically use a good representation for it. So for instance, for all your finite element simulations, you will use a sparse representation. I don't see another question. Let's see if we have more questions here. Yes, I got the question if the type of linear solver here is what I guess you're asking, does it affect my accuracy? That's a good question. The direct solver is, as the name suggests, a method that solves the problem in one direct step. And for that, you normally get high accuracy, very high accuracy, as we're calling it floating point accuracy. But that is of course limited by the condition number of the matrix, but that's about as high accuracy as you can get. The iterative solver process is terminated at some point, and that can be tricky. It's not a problem to get high accuracy, but it's a problem to stop so that we don't waste resources. And COMSOL is doing a good job in finding the balance between the accuracy and performance there. So no, normally when your problem converge, you will not have to bother about this. But there are cases where extra accuracy can be needed for the iterative linear solver process. But it should not affect, you should not expect it to be affected. If it is, it's something wrong, and you can increase the requirement for the termination of the iterative process. Okay, good questions. So I got a question on memory buses. So memory buses, how do they perform? How are they characterized, and what is a good bus and not? Well, memory buses will naturally be improved by buying newer processors. You can expect a better memory bus, but if you really want to see, it is the access time of memory that is important. So how long does it take to fill my cores with new data from my memory? And that you can see in data sheets if you really want to compare. But it's a good question, because looking at memory buses and their characteristics are more important than looking at the clock frequency and the number of cores of your processor. So that's a good question. I will now take more questions later. I will go to cluster computing because I think you want to hear this. Cluster computing is about connecting multi-core processors with a network. And the interesting architectures are the one with high performance network. If you have a too low speed network, you will not get benefits of using a cluster. It requires a floating network license. You can start a cluster job from a GUI client by using a cluster study, and then you can monitor the job from that client. You can start a batch job from the command line directly on the cluster for any MPH file. And the third option is to start the whole desktop on the cluster machine. And we have blog posts about this. So communicating now between those processors can be very complicated, and the motivation to go to a cluster is not primarily to solve the problem faster, but to reduce the peak memory use for any of these cluster nodes, so that I can solve a larger problem. Basically, when you run out of memory, when you have done all the things on my previous slides, and you still want to solve the big size problem, then a cluster can be a solution to do so. There are other ways to use a cluster for speed. For instance, if your model fits in a node, fine, but you're solving a lot of similar problems in a parametric sweep context, then you can use for either the distributed parametric sweep or something called cluster sweep to get speed up also in that situation. And COMSOL can combine these two type of parallelism so that you don't have to disable any multi-core parallelism, but on these cluster nodes, you're still running multi-core processes, multi-core parallelism. So we have what's called a hybrid model for parallelization. So everything that you think of are expensive are parallelized distributed, as we say. Distributed means here that the data involved are stored on distributed, not on, so one node in the cluster is not having access more than a fraction of the total problem size, and that is important, especially for the big data structures like solution vectors, matrices, and data structures related to these things. And here is an illustration of how important it is to use a high performance network for the cluster. There's a comparison with simple Ethernet connection and InfiniBand, which is a high performance interconnect. And you basically don't get any speed up by using Ethernet. The communication on the Ethernet will prevent you from getting good performance. So let's go to real examples and benchmarking now. Let's take to look at stationary CFD, which is an important application area, by using a cluster. What can you expect from that? We have two good technologies for that. First of all, multigrid with algebraic multigrid as preconditioner works really well. So that is already a good technology for multi-core computing, but it also works fairly well on cluster. And then we have another technology that we worked on for a long time called domain decomposition, where the problem is split up in a little bit different way. But the way to see that is that the preconditioner here for multigrid has been moved down. This is at least a natural candidate for using domain decomposition, is to move down this preconditioner option or setting to the domain level as a domain solver. You see here that the multigrid is moved down to the domain solver, and then we have a core solver here using Paradiso. This gives benefits. So let's look at the benchmark in CFD. You have this model in at least the CFD modules application library. We have here sold a refined version of that to better capture the benchmark results. It comes up to 6.3 million degrees of freedom, converges in 117 segregated nonlinear iterations. First, look at the CPU time for multigrid, the multigrid option. Notice here that on the x-axis we have the number of cluster nodes used. So we have tried on 1, 2, 4, 8, and 16 nodes. And we are comparing the version 5.4, 5.5, and 5.6. And you can see here that we continue to improve the performance also for this release by improving basically the preconditioning technique. So this is without domain decomposition, just standard multigrid. Basically taking the same solver technology used for multi-core computing to a cluster. Showing that all these methods are working under the hybrid parallelization model. Memory requirements have been improved even more in this release. You see here the yellow line here is the latest release, and you see here a nice slope now. We didn't have as much improvement in memory before, but now we can motivate more to use a cluster for multigrid by getting this nice effect. If we bring in domain decomposition to the equation, compare the dashed lines here are numbers for the CPU time for the domain decomposition. Blue curves are for 5.5 and yellow for 5.6, version 5.6. And what you can see here, not only that have we improved multigrid, but we also have improved domain decomposition. And I would say even more, because the margin now in CPU time to multigrid is substantial for all problem sizes, except for one node here, which we think is due to poor load balancing and can be improved further. But for all cluster number of nodes 2 and up, we have some margin to the multigrid results. So we have a better solver technology now than ever. But we also, important, we can beat the technology we're using for standard workstation. So when going to cluster, the domain composition is important. I will show you soon a new option, an operation where you can convert your existing solver to domain composition configuration. But before I do that, I will go to another example. Here is how the memory numbers behave. Multigrid is still the better alternative for this test. We believe we can change this so that also for domain composition, we can, so also for memory, we can beat multigrid for this problem size. Notice, however, that the memory gain is growing faster for domain composition than multigrid, which almost levels off here. Here, the yellow solid curve, while we have a more negative slope here for the dashed yellow line. And compare also the difference from earlier releases. So we might actually be there already if we had more nodes to compare with here, but we haven't done that yet. So I will, before I show you the convert to domain composition, I will give you another example, because in many cases, iterative linear solvers are not an option. You have to stick with the direct solver. Here is an example from the semiconductor module, where the coupling is strong, the nonlinearities are difficult, and they have to stick with the direct solver. Luckily, direct have cluster support, so we can compare this now using MUMP's cluster support, where the LU factorization is done in a distributed fashion, with our domain composition technique, where again, the linear solver MUMPs here is moved down to be used as a domain solver. It means that on the domain, we see a much smaller problem. It's typically a one domain per cluster node is a common setup. And in this case, we are not using a core solver for domain composition. So domain composition is only solving these domain problems in parallel. On top of that, we have an iterative solver. How does that compare? The dashed line again are domain composition number, and the solid is the direct solver, MUMP's behavior on cluster. So this is a finite element formulation. It works well for the default finite volume formulation as well. We wanted to show here that it carries over to finite elements as well. These nice results, you see that already for one node, we beat the direct solver by using domain decomposition. So 16 domains are used for all the simulations here when we talk about domain decomposition. Another way so you see here the CPU time on top and memory behavior on the bottom. So both show very nice effects of going to a cluster. Just some numbers. So we have two sizes of the problem. One is 16 million degrees of freedom. Let's see now. No, sorry, this is the 2 million size problem, and then a finer version. For the finer version, 16 million degree of freedom, MUMPs is not feasible anymore. But with domain decomposition, we can use 16 domains and get the problem through in 9 hours using one node. But with 16 nodes, we get it through in less than an hour. And we use almost a tenth, we'll use less than a tenth of the amount of memory by going to 16 nodes. And here is another way to look at it with speed up and memory gain. You see here also that the yellow curve is the bigger problem, the 16 million size problem, and the blue are the 2 million size. The solid is the MUMPs, the dashed is the domain decomposition behavior. You see the memory gain and the speed up numbers are much better for domain decomposition And you see also here that the size makes it even more advantageous to go to cluster. I'm almost done. We have used 55 minutes. I will just notice that there are other ways that the model can be big. For instance, if we solve many versions of a model and we want to save that, or we want to solve them in series, and then they will become expensive. And what do we do if the data is just prohibitively large to store? Well, there are a few things you can do. For instance, you can disable the storage of individual fields, go into the field node and uncheck store in output. That will reduce the file size. But that, of course, assumes that you don't need this for post-processing. You can you use the other fields, or you can use some global quantity that is enough. You can also disable storing the full field. You can so to say store on certain selections that you control on the study node, for instance. So in this scenario, you will only store the fields for the lumped ports, port 1 and port 2 here. Everything else will be discarded. A third alternative is to use probes to only store global quantities in a table format on file or in the model. You have keep solutions in memory when you're doing parametric sweeps, where you only store the last one. But to get access to the full solution, you can store them on files and then open them individually. That's a way to make the individual MPH file smaller. But then, of course, you have a number of other files for the individual results. To sum up the presentation here, we have looked at different solver technologies that affects memory and CPU time. We have looked at benefits of using multi-threading or multi-core computing on modern CPUs. I have showed you 2 examples where cluster can benefit your simulation in terms of most importantly, the memory requirements. The memory peaks comes down, but you can also get nice speed up effects. But remember, the peak memory is the key here. You don't expect to get speed up in CPU time in all situations going to cluster. And then I've pointed to ways to lower the memory requirements on especially for multi-core computing. And then I hinted also a way to avoid the MPH file being very large. You can reduce the size by disabling certain type of storage. What I have not covered is to use COMSOL to solve problems that fit into your multi-core processor, and you want to solve a lot of these problems in a parametric sweep way, but you want to get speed up. And that can be done in a number of ways. Parametric sweep is one way, distributed parametric sweep, batch sweep is a second one, and cluster sweep. I have slides that you can download from this presentation showing these things. Notice in particular that batch sweep can be run without an FNL, and you can use the simultaneous processes to do these jobs in parallel. And that you can do on your own machine, assuming, of course, that all these processes fit into your memory. But that's an option that can be worth checking out if you don't have an FNL. That finishes my presentation. I will go over to your questions now. Let's see here. Go up and let's see here. See if I can see the questions here. Sparse, and we answered. Assuming that I have 48 cores on my machine, should we specify the number of cores or let COMSOL choose? If you're not doing anything else on your machine and you want highest performance, I would just go with the default, which will mean using all these 48 cores. More memory can lead to lower performance. Yes, that is actually something that is true. And the reason for that is that when the CPU or the memory banks are populated like this, then the bus can run on highest speed. But there are effects on some motherboards where when the banks are fully populated, then the bus is degraded to a lower speed. And I think that has to do with heat problems, because you can imagine that if you have more memory banks in here, you generate more heat just by driving them, and the bus and you cannot run the bus at the same speed. So that is something you should consider when upgrading. That upgrading memory, avoiding using all the banks is better than filling them up. So it might actually be advantageous to remove these and instead put back memory cartridges with maximum size. But again, check the specification, follow those for the processor you're using. Thank you for that question. Yeah, I got the question on how discretization order affect the acoustics module and acoustics problems. It's a bit of a different question. I will higher order for acoustics problem, wave problems will be normally affects the efficiency, but by just increasing the order, you will get the more coupled problem, as less bars and more difficult to solve for. So you have to use that in combination with a coarser mesh, and a coarser mesh for wave problems. Then it's important to still resolve the waves. So it's a tricky balance, but I can say this, that higher order for wave problems pays off. So linear order should not be used. Second or third order should be used. Maybe even higher. In structural mechanics, what is generally more efficient for an accurate solution, increasing the number of elements or increasing the discretization? That is a good question. And structural mechanics problems are tricky, because the tricky part of structural mechanics problems is that accuracy is typically determined what happens on the boundary. So if you have corners, if you have edges that are sharp, etc., that requires extra care. And I will not give a definite answer to that, but for complicated structural mechanics problems or demanding problems, I suggest using adaptation, mesh adaptation, to find at least a more efficient mesh than the default one, because the default one is not using any information about the solution, only about heuristics regarding geometry representation. To some extent also the physics, but in structural mechanics it's not easy to do without looking at the actual loads and stresses. I will continue here answering questions. We have passed the hour. I know that, but there's a lot of questions. See here. Yeah, I've got a lot of detailed questions on your particular problems here. Not have time to go into that. So I'm trying to find general questions. Oh, this is a tricky question. You mentioned before that increasing the number of cores, that reduces the solution time. Between this and reducing the mesh size, which one does significantly reduce the computational time? Well, reducing the mesh size will make the problem smaller, and for all technologies that will be easier. All solver technologies that will be easier. But the drawback with coarsening the mesh is that the accuracy and even the robustness can be affected negatively. So I wouldn't say that choosing the number of cores and the coarser mesh is in any way in conflict with each other. They are very different, and using cores is basically for free with COMSOL. You don't pay anything extra for using all available cores. So in the I see no reason why you should not use the maximum number of cores. The only reason I can come up with is the memory effect, that you will use a little bit more memory for it. But there are two very different questions. Okay, I got a question about between the direct and iterative solver, which one is mostly used and yields the best accuracy? Again, accuracy is not really an issue. You should expect the same accuracy from iterative solver as for direct solvers. There are exceptions to that, very ill-conditioned problems, and non-standard matrices. We might not even be able to solve them with iterative solvers. But when they work, you should not expect any degradation of accuracy. Mostly used, well, that depends on which area you are working in, and we can maybe answer the question by looking at the default solvers used for your particular module. In CFD, for instance, iterative linear solvers are very standard and the default and the most used. For structural mechanics, it's the other way around for different reasons. One reason is a very it's a common with highly nonlinear material models. They're using direct solvers, but they also add, as we saw here, disabled iterative solvers. So it depends a little bit in what area we are looking in. But eventually, I would say anyone doing large-scale computing need to consider iterative linear solvers. So it's just a matter of size before you need to use them. That's my view of it. There are some exceptions where you can, for instance, go around the problem by using domain composition, as showed you here. But that is, in essence, formally, it is still it's an iterative solver using a direct solver on the domain. So it's sort of hybrid case. But if you're working 2D axis symmetry, for instance, if you can get away with that, you can stay with direct solvers. They are very easy to use, and you. So it's a bit like going to cluster. Eventually, you need it for just for performance reasons. Thank you. Using the cluster computing in a local GUI, if a simulation on the cluster is stopped because of the time limit, is there a way to continue the simulation? Yes, there are ways to stop, to continue a simulation that has been either crashed. That will be possible to restart it, or if it reaches a limit for other reason. There are ways to do that, but the recovery feature needs to be enabled. That can be disabled, but it should be default enabled. And how can I be sure that my machine is able to solve the problem before starting the analysis? That you cannot be sure. I would not even be sure of that if you're giving me all the input data. You can do a qualified guesswork by, for instance, studying as we did here initially with these type of graphs, by looking at trends, and you will have a behavior for your type of physics, for your formulation, and from the solver technology. All these three things affects the behavior. And the CPU time is similar. You have or you can do similar predictions by refining the mesh. But without knowing much about the problem in detail, it's very difficult to predict. But I hope I have convinced you that there are a few key ingredients into this. When running several instances of COMSOL without specifying the number of cores, will they detect and adapt dynamically the number of cores used? Well, that's a good question. No, they will not do that. They will not care of, when you start COMSOL, they will not consider what else is done on the machine. A common problem is when you're running on a big Linux workstation or any kind of computational server which are shared among different users. So the COMSOL does not consider other processes, not even your own processes that are already running. So you will use the maximum physical number of cores in each instance of COMSOL. So this is actually another situation where you might want to downgrade maximum number of cores to a lower number. And doing the batch sweep on the same on your own machine, your own local machine, is also a situation where you might want to use less cores for performance reasons, because they will otherwise just compete with the same resources, and you can even get a down decremental effect from using all cores for simultaneous processes. So that's a good question. Okay, we are at least 15 minutes over here, so I don't think I have time to go through many more questions here, but a lot of good questions. Thank you for all your attention, and that will conclude the presentation. Thank you.